Hi, this is Nuria Torres Alba, currently working at Clemson University on a complete census of heavily obscured supermassive black hole accretion in the nearby universe. An obscured AGN is an AGN that we are observing through the torus of gas and dust that surrounds it. This torus mostly obscures the emission in the optical to UV range, but in fact, if it's dense enough, it can even obscure the X-rays that are coming from the corona. Here I am showing how the X-ray spectrum of an AGN changes as a function of the column density in our line of sight. At column densities that are larger than 1.5 times to the 24 per centimeter square, almost all of the X-ray emission below 10 keV is completely suppressed. We call this type of sources Compton-Thick AGN. But why do we care about Compton-Thick AGN? Well, this is because we actually need them to explain the peak of the cosmic X-ray background emission. In order to properly explain it, population synthesis models estimate that between 20 to 50% of all AGN in the local universe need to be Compton-Thick. But in fact, observations are showing that only between 5 to 10% of known AGN in the local universe are Compton-Thick. So we know that there are a lot more Compton-Thick AGN around us that we actually can observe. But how do we fix this? Well, in order to properly study this, we have started the Clemson Compton-Thick AGN project. And our objective is to find and characterize all the Compton-Thick AGN in the local universe. We do this using the SwiftBAT catalog. SwiftBAT is an X-ray observatory that monitors the whole sky in the hard X-rays in the 15 to 150 keV range. This is the range shown in this plot in pink. And as you can see, this range is not easily obscured, even by the highest column densities in their line of sight. However, we cannot follow up every single AGN in the BAT catalog with soft X-ray observations. We need to know which AGN have a good chance of being obscured. We do this by selecting these AGN that have been previously classified in optical as Seyfert 2 AGN and that are at the same time not detected by ROSAT. As you can see in this plot, sources that are not detected by ROSAT have already a good chance of having column densities higher than 10 to the 23. Following this selection criteria, our previous works have shown that we have a 50% chance of finding a Compton-Thick AGN in the local universe. This has to be compared to the fact that in a blind survey, only 5% of sources actually turn out to be Compton-Thick AGN. Once we do this soft X-ray follow-up, we can do a first preliminary analysis. And using it, we can already see which sources don't look very obscured, like the one shown here above, and those that look actually like very good Compton-Thick AGN candidates, like the one here below. We do a further follow-up of these very good candidates using simultaneous XMM and NuSTAR observations. We have recently been awarded simultaneous NuSTAR and XMM observations of 10 new candidate Compton-Thick AGN in the nearby universe. These 10 AGN were the only ones out of a sample of 50 but selected Compton-Thick AGN candidates that were lacking NuSTAR observations until now. And using these simultaneous observations, we can estimate properties of the AGN to fully characterize it, such as the photon index, the obscuring column density of the torus, both in the line of sight and in average, the covering factor, or the inclination angle. And actually, we have successfully performed this characterization for all the rest of sources in the sample and published the results before. We also characterize sources that are not Compton-Thick AGN, and for that, please tune in to Shuri Zhao's talk in this very same conference. And in here, I will leave you with my conclusions and just remind everyone that all the details on the project, including the published papers, results, and the best fit models for all of the sources that we have analyzed, can be found in our website.